Hi. In this session, I just want to talk about how shear force in a beam is equal to change in the bending moment with respect to x. Consider here a beam under uniform distributed load, and I select a very small, tiny length of the beam, an element of the beam, incremental length of the beam, as delta x. And I draw the bending moment for the beam as well. Then this is a parabola shape for uniform distributed load, omega. In this case, for this element of the beam, I show internal reactions in both sides of the element. These sides M and V, and bending moment, V shear force, the part of the element that is subjected to the distributed load. And the other side of the card, we have a V and M, and the direction that I choose U is the convention. For the right side, actually V upward, M clockwise. For the left side, cross sections, M counterclockwise, and V downward. But the V in both sides are not equal because of the external load that applied uniform distributed with applied here. We just show it with an increment change in shear force. We call it delta V. This delta V doesn't mean that it is positive or negative. It can be any positive or negative. It depends on the situations. Well, because you may assume that, okay, this force must be larger than this because this is also in the direction of this. This equal to this plus this, that this delta V should be negative. Yes, you are correct. But I told you that delta V, V plus delta V is larger than the V. No, it can be smaller than the V. It can be delta V is a change. That this change can be a negative. Okay? Then we just show it with added something negative, added something negative. Other side, actually the same story for bending moment M. M in this side, we call it M. The other side, M is different. You will see that's the M, and here is M plus delta. Delta M here is a positive increment, actually. As the curve show, diagram, bending moment diagram show that M and M plus delta M is completely different from each other. I mean, delta M here is a positive. Okay, then write the equations of moments, equations of equilibrium for moments at C. See what we have. Let's write the equation. Sigma M at cut section C is equal to 0. Summation of moments above at cut section. In this section, I have M clockwise, negative direction, clockwise, we put negative, and we take moments about these sections, and V times this distance delta x, clockwise again, minus V delta x. And here, we have a uniform distributed force in equilibrium. We must convert it to a point load. Equivalent of this is a point load, acting in the middle of the rectangular form of the uniform distributed load, and it is value is omega dot delta x. This value, and it acts in the middle exactly, and this distance is delta x over 2. Then the moment of this one, which produce a counterclockwise moment plus omega delta x times delta x over 2. And what else we have at this here? We have a moment m plus delta m, which is counterclockwise, positive, equal 0. Then we can spell our loading conditions that produces bending moment, and then we simplify that. We can cancel out minus m with m, and I rearrange it, delta M minus V delta X here plus omega over 2 delta X to power 2 equals it. Because this is an incremental value, math, and it as a power 2, we cancel it out. It's very close to 0. Get rid of that. Some assumptions. Then we have delta M minus V delta X equals 0, or delta M equals V delta X, or V equals delta M over delta X. This is why in some video, for this ratio, we always say that delta M over delta X, or derivative of M with respect to X, if you write the equation of bending moment in terms of X, is equal to shear force. And this is the relation between bending moment and shear force in a beam. Thank you for watching. Bye now.